Here's video 1 for chapter 13, which is on solutions. So what a solution is a homogeneous mixture. And if you recall from the beginning of the semester, mixtures are a combination of two or more pure substances together. And homogeneous means that it needs to be a mixture that has the same composition throughout, meaning if you have a beaker of salt water and you have stirred it, then that would be a homogeneous mixture, which could also be called a solution. Whereas if you have sand and water, no matter how much you stir, that would be a heterogeneous mixture. It would not be the same throughout, and so that would not be called a solution. So salt water is one example. Coke or any soda would be another example because it's the same throughout. And mixtures are made up of solutes and solvents. The solute is the minority component and the solvent is the majority component. For example, with salt water, water would be the solvent because there's more of it, and salt would be the solute. For Coke, the solvent would be water because that is the majority component, and then there's multiple solutes. There's many more than this, but I just mentioned a few. That carbon dioxide would be a gaseous solute. Sugar, if it had normal sugar, would be a solid solute, or if it had the fructose corn syrup, that would be an example of a liquid solute. So you can tell there's multiple solutes here that are dissolved in water. We understand that there's this principle that says like dissolves like, and this is all based on intermolecular forces. So for things to dissolve in one another, they must have similar intermolecular forces. So if they're both polar, they'll like each other. If they're both nonpolar, they'll like each other. So here we're looking for things like hydrogen bonding, dipole-dipole, ionic compounds, etc. I'll show you a few examples. So here you've got CH3OH. We notice that it's both polar because it doesn't have the same surrounding atoms around carbon. So it has dipole-dipole. It also has hydrogen bonding. And we know water also has dipole-dipole and hydrogen bonding. So these two are similar and will dissolve very well in one another. NaCl is an ionic compound, which means it does have charges, a plus and a minus. Water is polar, and therefore, since it's polar, it has a partially positive side and a partially negative side. So what we want to know is that polar substances like ionic substances because they both have charges with them. And this specifically is called an ion-dipole attraction because water is a dipole, meaning it's polar, and then NaCl has actual ions in it. So there's an interaction here where the two like each other. And then the last one, C3H8, anytime you have a compound that is only C's and H's, you are automatically nonpolar. So C3H8 is nonpolar, only London dispersion forces. And then there's water, who is very polar, has hydrogen bonding, and so these two will not mix. They will not be soluble in one another. When things dissolve, what dissolving means is that one substance just spreads throughout the other. But if you dissociate, which is this next word, that means not only do you distribute, but you also break into your individual ions. So here the definition is when a substance breaks into ions when it is dissolved. So you could be a strong electrolyte, a weak electrolyte, or a non-electrolyte. If you are a strong electrolyte, what that means is every compound that goes into water will 100% break into ions. What that means is there's complete dissociation. It completely breaks into ions. It's also a very good conductor of electricity because it is made up of a bunch of ions. So here, for example, HCl, as soon as it breaks or gets to water, it will break into H plus and Cl minus. We use a single arrow here to show that every single HCl will break up. If you are a strong electrolyte, the way we know that you are is you are either a strong acid or an ionic compound. So a strong acid starts with H and it falls in this category right here. So here's the list of strong acids. Ionic compounds we know is just a cation and an anion. Weak electrolytes only partially dissociate, and what we know to be true is only about 5% of those molecules will break into ions. So 95% of them will stay together intact as a molecule. So you're getting very few ions here. And if you are a weak electrolyte, you are a weak acid. The way we're going to identify you as a weak acid is that you begin with H, but you're not on the strong list. So you start with H like an acid, but you're not up here in this group. So a couple of examples are acetic acid, hydrocyanic acid, hydrofluoric acid over here. And the way we note this is with a double arrow, because what it shows is not all of the HF gets broken up. Actually, most of it stays together as HF molecules. And we would say these are weak conductors because it's more so molecules than it is ions. Only a very few ions will be floating around. A non-electrolyte is when you have no dissociation. You can still dissolve and distribute, but you can't dissociate. So molecular compounds fall into this category where it's all nonmetals. So here, for example, if you have glucose, glucose could dissolve, that would be fine, but it won't break into any ions. So you'll notice that the molecule stays intact. So here, if we practice putting compounds into these three categories, we're listing whether each one of these is a strong, weak, or non-electrolyte. So calcium chloride, he starts with a metal. If you start with a metal, you're automatically ionic. Therefore, you're a strong electrolyte. HNO3, you start with an H, which means you're an acid. You go to your strong list. Nitric acid is on the strong acid list, so he's also a strong electrolyte. C2H5OH, that's all nonmetals, so that means you're a molecular compound, which puts you in the non-electrolyte category. HCHO2, formic acid, it starts with an H, so you know it's an acid. You go look at the strong list and it's not there, which means it is a weak acid. And if you're a weak acid, you're also a weak electrolyte. And then KOH, we start with a metal. So if you start with a metal, you're ionic and you're a strong electrolyte. This also falls in the category of strong bases. I didn't mention that here, but if you notice somewhere that it says strong bases or strong electrolytes, that is true. We are just going to go ahead and say if you are a ionic compound, then you will be a strong electrolyte. Here's another example. Here we've got 0.1 moles of each of the following compounds dissolved in 1 liter of water. So we have the same amount of each of these in water. What we want to check and see is, are they strong, weak, or non-electrolytes? And then we're going to rank them in order of increasing electrical conductivity. And it tells us that the greater the number of ions, the greater the conductivity. So first, let's just categorize them. Calcium nitrate. He's ionic because he starts with a metal. He's a strong electrolyte. C6H12O6. Glucose has all nonmetals. He's molecular, so that makes him a non-electrolyte. Sodium acetate starts with a metal. He's ionic, strong electrolyte. Acetic acid starts with an H, which means he's an acid. He's not on the strong list, so he's a weak acid and therefore a weak electrolyte. So right off the bat, you look for who makes no ions. Well, that's glucose because he's a non-electrolyte, so he's not going to be a conductor at all. I'm going to put him as the lowest conductor. Next would be a weak electrolyte because remember, he only breaks up about 5% of his molecules. So we've got acetic acid here as our weak. Then we have 2 strongs that we've got to rank. So what I did further here was figure out how many ions would be produced. So calcium nitrate, if he 100% breaks up, you get 1 calcium and you get 2 nitrates, which means for each of these compounds, you get 3 ions produced. Whereas for sodium acetate, you get 1 sodium and 1 acetate, which only gives you 2 ions. So that means calcium nitrate will actually be a better conductor than sodium acetate because he has more ions present. There are different types of solutions that can be formed. There's saturated, which is where a solution contains the maximum amount of solute. So we know that salt dissolves in water, but at some point you can add so much salt that no more can dissolve and it'll just fall to the bottom. That would be called a saturated solution because it contains the maximum amount of solute. Unsaturated is kind of the opposite. It just contains less than that, meaning it can still dissolve some more solute. Then there's a third really kind of special scenario called a supersaturated solution. These are much more rare because they're unstable. But here the solution actually has more solute dissolved than the maximum amount. So the way this is made is you form it by heating up the solution and getting a lot of solute to dissolve, and then you slowly cool it, and that solute will remain dissolved. And so you actually have more dissolved than you should at that temperature. And it is unstable. It can easily crystallize. So that's a very specific scenario. There are several factors that will affect whether a substance will dissolve in a specific solvent. We've already talked about the first one here, where like dissolves like. And really, you can somewhat boil it down to polar substances will dissolve polar substances and ionic. Non-polar substances will dissolve non-polar substances. So it says which of these solvents will each of these compounds dissolve better in. Carbon tetrachloride is one solvent, and it's non-polar. And then water we know is polar. So what we do is just run through our list and decide which ones are polar and which ones are not. C7H16, remember the clue that if we have just C's and H's, that means you're automatically nonpolar. So he's going to dissolve much better in CCl4. Iodine also is nonpolar because it's two identical atoms pulling on electrons. It's also nonpolar and will dissolve in carbon tetrachloride. Sodium sulfate is ionic. And remember, ionic is just superpolar because you have complete ions here. So therefore, sodium sulfate, ionic compound, will like something polar like water. And then HCl is also polar because it has two different atoms pulling on electrons. Chlorine will pull more strongly, and therefore, since it's polar, it will also dissolve better in water. Pressure is another factor that can determine solubility, meaning how much will dissolve. So here what we know is solubility of solids and liquids are not changed by pressure. So no matter how much pressure you provide, it won't change the solubility of the solids